Good morning, everybody, and welcome to CS264. This is lecture 13 in week 7. I have a lecture this morning on our first introduction to software design patterns. So over the next while, we'll be placing more emphasis on the design and less on code. Although we need to be able to get better at the code as we work through the module, but we now need to start thinking about what does that code look like, and is it the best possible design it could be. And so in order to help with that, we're going to look at some background notes on how to do design, object-oriented development, and then we look at design patterns. So it'll happen over this week and next week, I guess. So the first thing we're going to have a look at, I guess, is some discussion, and it will be ongoing, about OOD, and we'll be talking about SOLID today, and that's an acronym that's used to describe the first 5 object-oriented design principles. But before we do that, I just wanted to talk to you about 2 things. The first is about the lectures, and the second is about the current assignment that's coming up. So we have, I've been ill recently, I know some of you know, and so I'm a bit behind on some of the lessons. So I still have the link ones to do, and I have a design from last week to do. So my plan for the lecture last week is just to pre-record another 1-hour lecture and upload that one, and then that will help me catch up. I'll do that this week. And for the link demos, I actually have calculated some of the time that I've put into the lessons for you, and the time that you have to spend reading them and using them. So I found that I've gone about 20, maybe 25 minutes over the time that's allocated for that. So I'm working on reducing the lessons that I have for the link so there'll be 5 again, but there'll be 5 really short ones. They'll only be about 5 or 6 minutes, and that should equalize the work and reduce your workload in terms of the time you have to spend working and looking at CS264. So sorry about that, but some of the topics were hard and they needed some detail. So I gave it that detail, but but on balance, I think we'll do a good job in terms of making sure that you're not overworked on that front. So the second thing I want to talk to you about was the assignment. So let me just see if I can get something for you. The assignment is interesting because it's a little bit more about design and some design patterns, and I have actually produced an example that will be very, very useful for you. So this is in week 4, okay, of some of the examples. And if you look at, and you may not have seen it yet, because of course it got up a little bit late and you were working on your current assignment. But if you look at this particular example, and let me switch so that I'm not overwriting it here. So what I have is this example that creates a canvas, displays the canvas. This is the kind of canvas that you used in your last assignment. I've added 4 circles to this canvas, okay, and you can see I've randomly generated these circles here. And so I'm adding these shapes, and I'm looking at the canvas again, okay, and you can see that this is the current description of the canvas. Now I'm deleting 2 circles from that canvas, and I'm issuing commands, and then I'm letting it be known what the command I received. Here, to delete commands. And this is the information that comes back from the command that's executed. And now my canvas just contains these 2 circles. Now, I know with your work, you've been looking at SVGs. But anyway, this is fine. So now what I'm trying to do is I'm undeleting the 2 circles. Okay? It's an undo operation. And I have, I'm back again to have my canvas again, as I would expect. Here. Doing some more undeletions and additions and so forth. And in the end, I end up with a canvas that looks like this, having had added. Now this particular one just these are circles. So I've added circles and so forth, and I've worked from there. So you can look at code here, Visual Studio Code. Let's get rid of that particular one, and I presume I have. Okay, let me just get this one back up for you. Okay, and so here we have the program, and you can see if you look in the demos, it's called my command. And what this actually does is it implements the command design pattern so that you'll be able to use that. Okay, now I did mention in the lecture, in the assignment, that you could look at implementing a design for undo and redo using either memento or command patterns. So if you go to the lesson and have a look at the lessons, I think this is 8.4, you should be able to see how I worked and explained how I wrote this program. So it's fine. I just checked. This is the one here. Yeah, it's lesson 8.4 and 8.04, and you can look at the video for that. It's on YouTube as well. Okay, thank you very much. So I just wanted to get to that and let you know that there is support for the current assignment currently online. There's a video, there's sample code. You'll be able to work with it in conjunction with the work that you've done in your last one. Okay, so we can try that. Okay, so I see there's a question coming in there from Aaron. So yeah, so you built an undo command which undoes the last delete. That's enough. You need to make it so that it undeletes any command, not just undelete the circle. So you might have a command where you delete, where you add or you change something, or add a circle or add a square or something. So you need to be able to undo, and you might want to redo those as well. And it's important, I guess, in that particular exercise as well, that you do implement it the design in a way that meets with a design pattern. So there's two approaches to do that. And if you have a look at the lesson and the notes, it'll show you how to do that. It's a good question, Aaron. And actually, we can come back to this in the tutorial as well tomorrow. So we don't have to do it in the lecture. I take up some of the lecture time because I do want to have a look at the solid principles. But yeah, if you've other questions, add them there and to the chat, and I will get to them. Okay, thank you very much. Right, so we're going to look at solid, and we're going to look at talking about solid then today, and we are. It refers to 5 important design principles. Okay, when conducting OOD, and the principles were introduced by Robert C. Martin, who's you'll see references to Uncle Bob, in a paper online. In this paper called Design Principles and Design Patterns in 2000. The SOLID acronym itself was introduced by Michael Feathers. Okay, so SOLID stands for it's an acronym for a bunch of principles, guiding principles for OOD, and it stands for Single Responsibility Principle, SRP, Open Closed Principle, OSP, Liskov Substitution Principle, LSP, Interface Segregation Principle, ISP, and Dependency Inversion Principle, DIP. So these principles then, when combined together, make it straightforward for a developer, to develop software that are easy to maintain and extend. In other words, they're good design. So if you sometimes say, well, what's a good design, John? Then yeah, I would say to you that it's one that's got easy to maintain and also easy to extend. In other words, how you might change, and extensions means by changing. So sometimes maintenance refers to fixing things, and extensions refer to updates, adding more functionality. So in practice, actually, that means that the principles provide us with approaches to move away from tightly coupled code and poor encapsulation to a more desirable design where we have loosely coupled code that is encapsulated and that meets modern requirements. And we saw a little bit about encapsulation and so forth when we talked about the UML there recently. Okay, so we're going to take time in this lecture to work through the 5 principles. So the first one then, and in fact, I'll give some code examples for 3 of the principles, and in the next lecture, I'll do the remaining 2, okay? Because they're a little bit more complex. And that's point 3 and 5, okay? So first of all, we look at the Single Responsibility Principle, SRP. So this principle advises that a class should have one and only one reason to change. That means that a class should really only have one job. It does one job and that's it. And so then if it changes because that job has changed. Okay, you don't want to have classes that do 2 or 3 jobs, and then they change every time one of those 3 elements change. So in other words, don't have your classes do many things. They should be responsible for a single task. Now you might say to yourself, oh, this means I've got lots and lots of classes in my file, in my document, and they're very small and they're good. Okay, good. Don't worry about that. So the principle makes software easier to implement ultimately, and it prevents unexpected side effects arising from future changes. And remember, guys, you're going to be working in the lab with small enough classes, maybe 4 or 5 classes max, hundreds of lines of code. But what happens when you're dealing with like thousands of classes and millions of lines of code and keeping an eye and track on things? You can have, you can't be, you can't leave any of this to chance. You will have to make changes. You don't want any side effects, and it's really important that each class has this single responsibility. So the more responsibilities that your class has, the more often you're going to need to change it. Okay, and if a class implements multiple responsibilities, then the classes are not really independent of each other. Okay, so you don't roll all the tasks into one. It might seem like a nice thing to do, but don't do that. Okay, please. That should be your executable, where it uses all of the classes, okay, in some respects. So classes and other components then that have one responsibility are much easier to explain, they're easier to understand, and they're easier to implement than the ones that provide a solution for everything else. And we saw that when we developed REST APIs in CS230. It was a good design then, and it's appropriate now. We decided on this design. So adhering to the principle that you already know, and I'm sure many of you do it already, it reduces the number of bugs, it improves your development speed, and generally makes software development easier for you. Okay, so let's have a look at an example here. Okay, and here's one we want to look at, where a class should have one and only one reason to change, meaning that a class should have only one job. So that's just a reminder of what we mean by SRP. Say we want to calculate the area of a collection of different shapes. Okay, so say we have 2 shapes, and note that there are no constructors here. Okay, I could have set up a constructor, of course, if I wanted, but I'm just using the getter and setter and properties, and of course it's mostly because it's shorter to write. Okay, good practice to have constructors as well, of course, but I'm being lazy. So now let's say we have an area calculator on the right hand side. Now you may have done work like this, and you may have seen me do something like this as well in class as well, but and maybe I did something different. So we're going to have this class called area calculator, and it calculates the area of an array of shapes. Okay, and these shapes are independently of each other. I mean, we call it circle and we call it square, but they're not related in any way. Okay, not at all. I mean, it's not like we set it up and created a design where we have a shape class and then they inherit from the shape class and do all that kind of stuff. None of that kind of stuff is going on here. These could be called bananas, and circles. It doesn't matter. Okay, and actually the area calculation here, okay, that just takes a bunch of objects. Okay. In an array, and we will assume that somewhere we will have created a shapes array which will be of type object, and then we will have signed, as part of that creation, we would have created a whole bunch of these square and circle objects. Okay, so the total area is 0. And here we have the calculation. We just have this loop. So we iterate over the shapes, and we say if the shape is a rectangle, then we calculate the rectangle using this particular formula. If the shape is a circle, we calculate this, and then we return the total area. And you might ask, why are we doing this? What's the story with that? Why would you even consider doing this? Well, you might be building a pattern. You might be engaged in clothes manufacturing, and then you might have lots of shapes for the various components of a pattern for an item of clothing, and we want to be able to calculate how much material it costs, for example, in order to build that particular item of clothing. And we can there'll be different shapes when we calculate this. Generally we can always describe shapes in terms of triangles, I guess. Most of irregular shapes can be lots of triangles in which we can calculate. So it's a useful thing to do. Okay, so this works. Okay, there's nothing wrong with this in terms of it works, but we have to say, when we think about our designs, we have to go back and look at our code and say, does the code violate any of these core principles in Solid? So does it violate the single responsibility principle? Okay, so in order to use the area calculator class, again, we have to instantiate the class, pass an array of shapes, as I said here. Already we can see this one here. And so we could display the output down to the console in a fairly straightforward manner. And we got to ask ourselves then, and this works, looks like it's fine. We got to ask ourselves, is there a problem with this design? And this is the question that you need to keep asking yourself and thinking about when you write your code. Okay, you have to say to yourself, is there a problem with this design? Is it a good design? Is it a bad design? Can I improve the design? And sometimes people think improving the design changes the layout or the names of the variables that you will use and all this kind of stuff, but we got to ask ourselves, is there a problem with this design? Well, the problem here is that the class area calculator handles the logic to output the data. Okay, so we can see here. You may or may not have thought about that. You may have done. But if you want to chip in at any point when I ask a question, what's wrong with the design, please do in the chat. Okay, so the problem here is that the output method that the class is using handles the logic to output the data. So here we have our example that we had earlier combined into one. So here we have our object, which is an object array, and it contains a bunch of shapes: circle, circle, rectangle, rectangle. We calculate the area for this, and then we output the total area. Now, the outputting here may be contained inside of a method within the area calculator itself. So this line here, console.writeLine area, that could be in the class itself, could be elsewhere. But what happens if we wanted to actually output? So this just gives us the output here. So, and we've formatted the output, as you can see as well. Okay. What would happen if the user wanted to output to the data as JSON or HTML or some other format, for example? What would happen is that we need to add more methods. So what this means is that our class that we had previously, our area calculator class here, now becomes an area calculator and an output formatter. Okay? So it's doing two jobs. And you might say, oh, it's just writing. Well, actually, that's quite complex, because in modern applications, we tend to have complex work happening, and then we need to send the results somewhere. So you can think, for example, that if you were writing some backend Node.js app, for example, which I know you all are familiar with, then when you want to write something, you might want to write it to JSON, you might want to write it in response to some RESTful API, you might want to write the same data to a database, you might want to write it to a logger for error. So that whole writing activity that's going on means that the class is doing all this work, and then it's doing all of computing this value. In this case, it's an area. But then what's happening is that it is outputting that to all the various different places. So what happens is that we don't have single responsibility happening here. We don't have SRP. Okay? We're actually behaving as an area calculator, and we're behaving as an output formatter. And SRP tells us that the area class should really just sum the area of the shapes that are provided, and it should not care whether the user wants JSON or HTML, or in this case here, a string. We should actually create and generate an output formatter class, and then pass the information to this output formatter class, and then that does the work for us. So we can actually create an output formatter, for example, here. I haven't given the class to you. You could do this yourself if you wanted, and then we can actually do the creations and the information, do what we want to do. So it means that our area calculation just deals with area calculation, and our output just deals with output. So I don't know if that you may have decided that this didn't matter, okay, and that wasn't an issue in terms of the design, but actually it is, okay, and it violates the single responsibility principle. And you may have missed that when I came back and said to you earlier, is there a problem with this design? And you may have been thinking of something else. Of course, you may have been thinking that, yeah, there was a problem with this, right, as well, of course, but yeah, and good if you did. Okay, so that's the first one. So in summary, really, the principle states that if we have two reasons to modify a class, then maybe we wanted to update how we calculate areas, or we wanted to update how we output information, then we should split the functionality into two classes. So each class then will handle only one responsibility, and if in the future we need to make a change, we will make the change in the class that handles that update or change. Okay, so we could actually use interfaces as well to do that. So you'll see a lot of the time responsibilities happening with interfaces. So when we need to make a change in a class, having several responsibilities, we may actually introduce unwelcome side effects as a result of the change. Okay, in other words, it can affect other functionality that was unrelated to what we were actually trying to work. Okay, and in other words, the function, other responsibilities of the class. Okay, and you know, when we talk about responsibility, we mean, well, what does the class actually do? What's it responsible for doing for us? Okay, so the principle is an excellent way, really, of identifying classes during the design phase of an application. It should be provocative. You know, this particular principle is really interesting, and it should be provocative. It should get you thinking, provoke you into reminding you to consider all the various ways that a class may or could evolve with time. You know, it's really rare that you will write a class in an industrial application and that's it, done forevermore, that it's never revisited. Okay, so it does happen, and you do need to be able to work at that sort of stuff. Okay. A good separation of responsibilities will have been achieved only when the complete understanding of how an application should work following some application of SRP. So it's, you know, this is the first thing that you should be doing, guys. You know, you should be looking at your classes, you should be looking at your problem, looking at designing the classes, and then deciding what these classes will do, and ensuring that they're only doing one thing. And then when you have that sorted, you know, you're in a good place for starting coding. Do you have any questions on that? You can pop them in the chat if you want. We can always come back to it. No? Okay, the second principle is the open-closed principle. And you see it written open/closed, or you'll see open space closed or dash closed or whatever. Okay, so that's a principle for object-oriented design that was first described by Bertrand Meyer. And it says that software entities that are classes, modules, functions, etc., should be open for extension but closed for modification. Okay, that's a really nice phrase. Okay, and perhaps you get it, perhaps you don't. But if you don't, it tells us that we should attempt to write code that does not have to be changed every time the requirements change. Okay, and believe me, requirements will change. Real situations where you have real users, you know, they'll have changed the requirements 10 times in the spaces after taking us to lecture. Get this far in the lecture, okay? Always changes, you know, and that's part and parcel of software development. You know, the maintenance phase, we know from traditional models and understanding of traditional projects, you know, can take up to 70% of the time, the overall time of the lifetime of an application. So really, the design should be done in a way to allow the adding of new functionality, like new classes, and keeping as much as possible existing code unchanged. So we want to be able to do that. And so you know about this kind of stuff already. Okay, you've seen subclasses and all that kind of stuff, you know. So this may depend on the context, such as our programming language. When we're using C# or Java or other statically typed languages, the solution often involves using inheritance or polymorphism. Okay, and that's why we did that stuff last time in the last lecture on the UML, and we got to that, so we'll get that stuff. Okay? So the recommendation is that entities like classes, modules, methods should be open for extension, but closed for modification. So in other words, they should be easily extendable without modifying the class itself. So if you have a P class that works, then, you know, and it works all the time, and you're really happy with what it does. Now you want to introduce some extra functionality. Right? So what do you do? What's a good design? Do you get in and start making changes to the class, or do you extend that class with a subclass that includes all the extra functionality without changing the original class? And that allows you to be sure and confident that the existing software will work and continue to work, and that the extensions will work as well. Okay? Of course, that means that the new extended class needs to be able to do all the work that the other class did as well, you know, and it needs to be able to do that. In other words, you can replace it as a substitution. And that's why we have another principle, the Liskov one, which is the next principle, unsurprisingly, but we'll get to that. Okay. So if you're thinking along those lines, you're really thinking about the design. So let's have a look at our open and closed principle. So let's say we have this rectangle class, and that has a width and a height. So we're describing the rectangle with a width and a height. And again, no constructor here. I'm just using the getter and setter methods. In fact, you know, these are properties in C#. Okay. And you can do all of this stuff with Java as well. And you can do it with JavaScript too. And when you're writing your JavaScript, it's probably a good idea to start thinking about these principles, because they all apply and can be applied with JavaScript as well. Because, we deal with objects in JavaScript all the time too. So let's say then we also have this area calculator class. Okay, and that calculates the area of an array of rectangular objects. So last time we were just looking at general shapes, but now we're just being more specific and we're dealing with the rectangles. Okay, so we could, let's say we want to actually calculate the area of other shapes and not just rectangles. Okay. Let's say we started with this one, over here. We could modify the area calculator class to do that by checking the type of the shape using is cast to the type and calculate the area of the shape. In other words, is that a good design? So we think back to here. Now, last time we were interested in a single responsibility, okay, and that had to do with calculating area and principles. And you may have been thinking, I wonder, was that a good way? Was he talking about, is this a good design? Well, not in terms of looking at the class from a single responsibility principle perspective. But yeah, when we look at the open-close principle, this is another perspective, and that's when we get to start thinking about that particular class. Okay. So is it a good design? Okay, like I give you a hint. Most of the time I ask, is it a good design? It's not. Okay, and then we have to find out why. Okay, so what happens if we want to extend the area calculator class to calculate the area of triangles, for example? So it's or circles or whatever. It's not a complex task, but it could go on indefinitely. So you may need to actually do this. Even though it's a basic task, it requires continual modification of the code alongside. So, so we have it already set up to be able to calculate the shape of rectangles, calculate the shape of circles, and we now want to work with triangles, and we'd have to say if shape is triangle, then do this, and then we'd assume that the default one is a circle, but it's not all these, it'll be other. But what happens if there was some shape that was created? Because this was just an array of objects, and somebody could create an object that didn't actually have the information that we require, because it could be just either at runtime or compile time, be able to do something really strange, with that object. Okay, so what's happening here and what it tells us is that the class is not closed for modification, because we need to change it in order to extend it. Okay, so in other words, it's not open for extension. Okay, we do know a better way of doing this, of course. Okay, and that's, of course, to look at subclassing and class, and the best way, I think, or a better way to do this is to use an abstract class, shape, as the parent class, and that ensures that the subclasses implement some area method by the area calculator. Okay. Now, I mean, you probably do this already. Okay, and I'm sure you do it already. But I have seen instances looking at code where it's not done. Okay, and in fact, sometimes you find that you're doing something and it's good, and you can sit back and be confident and congratulate yourself and say, yes, great, I'm doing it correctly. But maybe that was an accident. Maybe it was, what you should really only be congratulating yourself if indeed it was a conscious decision to be implementing good design. Like people can be good teachers, but they may naturally be a good teacher. People may have to other people might have to learn to work hard, and they've done the work to make them a good teacher. So it's the same, and you might be good at sport because you've worked really hard. You might have natural innate ability and be good at sport as well, but actually it's innate. But sometimes you can always, even if you're brilliant at sports, then you can benefit from learning good principles and be better. So same thing happens here. Okay, so what we need to do is we actually will now look at this class shape, and we say that it needs to implement a method called area. Okay, and actually I've said here area calculator is closed for modification, actually opened up for extension. That should be shape. Okay, we need to change this to be shape. I was just copying and pasting to get the type. Okay, so now it's a much more robust class. So we have a rectangle. here that extend shape, and it calculates the area. And we have a circle that extends shape and calculates the area. And now our area calculator then, so will actually just be a much more straightforward one, okay, here. So we could actually modify this. Actually, well, we could say here, let me go back here. Okay, I'll do it this way. Well, that means now that means that this is correct. Okay, so this method is closed for modification. Okay, and open for extension. So it's okay. It's not too bad. Okay, so good. So using the open-closed principle, the problems from the previous design are avoided because the area calculator is not changed when a new shape class is added. So it's nice to do that. So furthermore, no unit testing is required. There's no need to understand the source code for that. It just works. It will always work. We can create new shapes to work, and that works fine. And as the area calculation code is moved to the concrete shape classes, there's reduced risk that old functionality will be impacted if new functionality is added at some later stage. You can see that we could create more classes over here and it would be fine. Doesn't impact on this. Since there are many design patterns that help with extending code without changing the code. Okay, for example, there's the decorator pattern. That's one design pattern that helps us follow OCP, the open close principle. And then there's the factory pattern, or the observer pattern, and they can be used to design an application that's easy to change with minimum changes in the existing code. And we're going to see these software design patterns in some later lectures, but we'll see them. Okay. I didn't mention earlier that about replacing a class with its subclass. The subclass needs to do work, and this is covered by the next principle, the third one, which is the Liskov substitution principle, and that was introduced by Barbara Liskov in a conference keynote called Data Abstraction back in 1987. Okay, so we've been thinking about this stuff for a long time. So Liskov then, with a colleague, Jeanette Wing, they published a paper which they defined the principle as let phi x be a property provable about objects x of type T, then phi y should be true for objects y of type S, where S is a subtype of T. So in other words, think of subclasses. Then really what this tells us in English, I guess, is that subclasses really need to be substitutable for not just is a. We often say, well, a subclass is a class. Class B extends A, class B is A. Well, really, what we want to be able to do is say class B is substitutable for A, which is what I was mentioning and referring to earlier in the lecture. So the principle defines that objects of a superclass shall be replaceable by objects of its subclasses without breaking the application. So that's what I'm saying. If you want to add this extra functionality, you should be able to do it without breaking the existing one, the existing function. That makes sense, though, I think. It makes sense. So it's a good principle, okay? It means, and actually it requires, that the objects of the subclasses need to behave in the same way as the objects of the superclass. And that's achievable by following some basic rules, okay? And that's why I'm going to deal with Liskov's substitution principle in another lecture a little bit later, okay? We haven't time to do it all here. I want to give you that overview, and then we go to a little bit more detail on this one. So we must ensure that all the new derived classes or subclasses only extend without replacing the functionality of the base or parent classes. Otherwise, the new classes can produce undesired side effects when they are used in existing program modules. Okay, so it's really important for us. It tells us that an overridden method of a subclass needs to accept the same input parameter values as the method of the superclass. Okay, that means you can implement less restrictive validation rules, but you're not allowed to enforce stricter ones in your subclass. Now that makes sense too, okay? And we'll see examples of this later, next time. Otherwise, any code that calls the method on an object of the superclass might cause an exception, and if it gets called with an object of the subclass, that becomes a problem, okay? Similarly, so this basically is the signature, and the return value of a method of the subclass needs to comply with the same rules as the return value of the method in the superclass, the parent class. You can only decide to apply even stricter rules by returning a specific subclass of the defined return value or by returning a subset of the valid return values of the superclass. So these are very specific rules and things that you can do and check, Okay, so there's no easy way. Okay, these are the strict rules, but there's no easy way to enforce this. And enforcement is always an issue. How do you know you've got good design? Well, you can just check it and see. That's down to somebody called you, okay? You as the developer needs to implement your own checks to ensure that your code follows the principle. So you can do this with code reviews and test cases. They're really useful for this purpose, okay? In other words, execute appropriate parts of your program with all objects of all subclasses to make sure that none of them causes an error or significantly changes the performance. And you have to do that kind of manually, okay? Okay. There's a lot in this list of substitution principle LSP, and we will look at some detailed examples of how to do that in the next class. Okay, let's look at the interface segregation principle, ISP. Okay, and that interface segregation principle was defined by Robert Martin while consulting for Xerox to help them build software for new printer systems. Okay, again, it's been around a long time. Okay, he defined it as clients should not be forced to depend upon interfaces that they do not use. Okay? And similarly then to the single responsibility principle, the aim of this one is to reduce the side effects and the frequency of the required changes by splitting the software into multiple independent parts. So instead of having one bloated, all-encompassing interface, many small interfaces are preferred based on groups of methods, each one serving one more submodule, in other words, functionality. And remember, you can implement as many interfaces as you like using C# and Java. So I see students, and over the years when they're designing software, they implement the class and then they implement some methods and then they bundle all of the possible things they might like to do or like a class to do into this interface. Okay, and then it becomes problematic because sometimes you want to use the interface. You might say, oh, really, I should have partially used that interface. And then so they end up having to, hack around implementing methods that they don't really need, okay, in their new update to the code, rather than going back and saying, well, like just replace the interface. But then you might say, well, this is provided for me, I can't do anything about that. Okay, so really you see this ISP used with SRP, and the two principles will strip a class of all variables, methods, or behaviors that do not directly contribute to the role. Okay. Methods must contribute to the end goal of their entirety. Okay, you don't include methods that you might use or be good to have later or something. They're really lean with this. Okay, so the advantage then of ISP is that it splits large methods into smaller, more specific methods. This ultimately makes the program easier to debug. In the end, it's much easier to debug these kinds of programs. Again, students will say, "But look, I've got loads of methods in there now." Well, good, yeah. Great. If each method is doing a single thing, and you can be sure that it will work, and it does that one thing, and there's no chance of a side effect, and it behaves the way you expect it to behave, well, great. Let's do that. Okay. Okay, so again, just a summary here that clients should not be forced to depend upon interfaces that they do not use. So let's say we wanted to work with 3D shapes in addition to the 2D shapes that we have, and we wanted to calculate volumes in addition to areas. So what we could do is we could have an interface called shape interface that we've been maybe using before and say, well, let's update our shape interface so that it actually calculates. We require a calculation of volume and area. But unfortunately, of course, this means that each class that implements this interface, like here, for example, a square, implements shape interface, it has to have an area and a volume. And if you have a cuboid, it also implements area and volume. Okay? That means that any shape implementing this interface must implement both methods. Okay. What's the problem with this design? Well, it's bad, and you can look at it and say, yeah, sure, that's obvious. But it's only obvious because you're looking at the names and understanding the names of the classes here. You're building this conceptual model in your head of what a shape is and what a 3D shape is. But these could be complex data structures that you don't understand, okay, just from the name. You don't really know, for example, well, we know that a square is 2D and it doesn't have a volume. because it's infinitely thin, you know. And then you might have a cuboid that has, like, you know, will have volumes, okay. And of course it has an area because you combine all the surface areas for all the various faces in the cuboid. So but it only makes sense. It makes sense that this is a silly thing to do, okay, or an undesirable thing to do, you know, a poor design, because you're thinking in terms of calculating area, volume, and interfaces. But if these were abstract computations, it might not be as obvious for you, okay. I hope that's clear, really, in some respects, that the naming helps in some ways. So it says that any shape that we create must implement the volume method, but we know that squares are flat shapes and they do not have volumes, so the interface would force the square class to implement the method that it has no use for, okay. You could say that the volume is 0, you know, because all flat shapes will be 0, but, like, you know, it would be best not to do that. So ISP then, the interface segregation principle, tells us or recommends that you could create another interface called solid shape interface that has the volume derivation. You know, solid shapes like cuboids can then implement that interface. So here we have our shape interface that does the area calculations. We have our solid shape interface that does the volume methods. And here, when we have a square, we say that it implements the shape interface. We're not saying that the square is a shape interface. We're saying it implements or does this. And the cuboid will implement the shape interface and the solid shape interface, because it will need to implement methods to calculate the area and the volume. Okay, I think that should make sense. If you think about it like this, using kind of models that you understand, then it can give you some sense of, you know, how you can get to have a good design. So we have dependency inversion principle next. And this one recommends that high-level modules, they often providing the more complex logic, should be reusable and unaffected by changes in the low-level modules. Okay. And this can be achieved by introducing abstraction that decouple high and low-level modules. Okay. So this is about abstraction and decoupling. So the best design for a class structure, therefore, is to begin with the high-level modules and work towards the low-level modules. And sometimes we talk about or hear about, so which do you do, top-down or bottom-up design? You know, top-down and bottom design. So, and I tend to favor the top-down design myself nowadays. But when, you know, in a former life, when I was doing my PhD in physics, I was writing software. I was building hardware controllers for observing. I was observing the atmosphere, you know, and I was building these camera systems that would look at the aurora borealis type lights in the sky at nighttime, for example. So we have to build that camera, CCD cameras. We didn't have controllers, so you had to build your own cards to put into your boards, and then you built the hardware. You created your own boards, popped them in, then you wrote your own controllers in assembly language, and then you wrote the Pascal or C code that would then manipulate those, and then you would try to map your modeling of what was happening in the upper atmosphere on top of that. So, you know, so there was a necessity at that point, you know, because everything depended on the hardware. Hardware reigned supreme then, you know, and you built all this hardware and you built all the chips, and these had controllers and you had to control the chips with assembly language. You know, you were bottom up, you know. But then when I was looking at from my physics modeling and trying to understand, well, you know, what's happening up in the atmosphere, you know, I was looking at a top-down approach. So I think in order to solve the problem I wanted to be able to do, there were two different kinds of problems. One is I need to be able to make the measurements, and then I need to understand and implement and ascertain what was going on. You know, they had two different kinds of pictures there, perspectives here. So you really have to think about, you know, the problem that you're dealing with, whether bottom up or top down actually works for you. So nowadays, I tend to look at top down because we tend to be looking at user type interactions with software, and I like to work that particular way. And I try to look at abstractions as I move, and then try to create abstractions that decouple the various phases of the work. And that's me in terms of my design, you know. So I tend to think about the high level classes that come from some UML model or UML design into some level of abstraction, and then some low-level classes. I tend to work with those after that. And, you know, you may have seen some of the example programs I give. Maybe the low-level ones may not have functionality fleshed out. They'll just be placeholders with just a message, a logger that says I've been called kind of scenario. But both kinds of classes then are the modules. They need to depend on the same abstractions. So sometimes I talk and I work with my students in terms of like if we have multiple students working on a front end and a back end, for example, we work on the abstraction for the model data that sits in between. And then, once that's fixed, then we can start working on both sides of that abstraction in some respects. So it's not good to have the low level working upwards towards something that will be a flexible design, okay? But if you think about my previous history, when I was building hardware and trying to control that hardware, I didn't need flexibility. There was no flexibility. It had to work this in a particular way. So it was okay to do it that way. But what happens if we need to replace a low-level class? Let's say I've replaced a chip or something. Then well, I would just have to get in there and write new assembly language. So that's how it works. But anyway, if we want to replace low-level classes, there are implications for all of the dependent code if there's no abstraction. Okay, and we saw that in CS230. We use JSON all the time for exchange between clients and servers, etc. We had fixed our JSON, and it didn't matter what the backend, whether we decided to we decided on a RESTful API, for example. We didn't matter whether we actually implemented that RESTful API in Node.js or PHP or Python or anything at all. It didn't matter. Java. With Spring, for example, the abstraction was there with the API, and the data model that was used to transfer it in JSON was fixed as well. So this abstraction you've seen before, and you're good at this stuff, okay? So you should be able to do this in your object-oriented design as well. So abstractions should not depend on details. Details should not depend on abstractions. These are the key points that you need to remember here. Furthermore, the design principle, this one, dependency inversion principle, the DIP, does not just change the direction of the dependencies as you might expect, because it's a dependency inversion. It splits the dependency between the high level and the low level modules by introducing an abstraction between them. So it's not saying that you flip them around, okay? It means that you split the dependency between high and low level. It's worthwhile doing that. Look, we look at this is a tough one again, I think, so we look at some detailed examples of this in the next lecture. Okay, so that's nearly the end. We're just at the end of about 50 minutes, and I'm trying to I've given you some longer lectures of late, and I'm trying to keep within the time, so I'm conscious of the fact that I can go on a bit sometimes. So we learned about solid. Well, we introduced solid today, which was the first 5 object-oriented design principles, and we saw how we might apply these principles that could lead to changes in our C# code. And I think that's very useful to know. We didn't look at the Liskov one in detail, and we didn't look at the DIP, the last one, in detail, but I will do that with some examples in a lecture, a separate lecture, which I'll record and upload for you. Okay. I'm happy to take any questions. We have a couple of minutes if you like, but thanks very much for attending this lecture. And gosh, it's a while since I did lecture 9. This is 13 now. So I'm quite happy to take any questions for a few minutes while I'm here, if there's anyone has anything. If not, then we can just leave it. And again, as I said, thanks a million for coming along, and good luck with your assignment. I'll pop into the tutorial tomorrow as well, see if you've got any questions. Benham knows about the lesson, and we should work from there. Okay, thank you very much.